So I hope everyone can see my screen now.
Yes.
Great. So as Dr. Tawfiq kindly introduced me, I'm Soroush Mokhtari, and I'm a postdoctoral research associate at University of Central Florida. And I'm presenting our research on classification techniques for pavement crack detection, pavement evaluation. I divided my material into different categories and sections. So I thought maybe it's a good start by the importance of the problem, why pavement evaluation is important for us, and a general overview on the structure of the methods that have been proposed to automate this procedure, which usually includes an image processing part, a feature extraction and feature evaluation parts, and of course classification, and at the end the rating of the pavement, which is very important. And of course our paper only concentrates, the paper that's published in TRB only concentrates on comparison of classification techniques. That's what I'm gonna go to more details, and then some final notes as future researchers. So basically nowadays all the states have pavement management systems which needs data from the pavement in order to be able to maintain the condition in a service situation, or in a good condition. For instance, in Florida, there are around 44,000 miles of road, which are almost all of them, 97% of them are flexible pavements. And although I'm talking about Florida, but most of the states are using similar system for evaluation or similar parameters. What Florida says is that 3 important parameters are there to evaluate the pavement: cracking, for rotting, and ride quality. From these 3, 2 of them, rotting and ride quality, are already automated, either with a laser profiler or the accelerometer on the vehicle. They can be calculated and measured very quickly at highway speed and very accurately. The only step that remained still very slow, very costly, very inaccurate and subjective is the cracking, and that's mainly because it's still manual. And the problem seems even worse when you consider that from 1994 till 2013, we constantly had more pavement because of the expansion of the road network. We had more pavement to evaluate, which means more manual workforce has to be used. But the manual inspection usually was conducted either through the windshield of the vehicle, so someone had to drive or walk by the side of the road to evaluate and record the defects. And after a while, the MPSVs, or multi-purpose service vehicles, came to at least automate the data collection part. And they are very effective. They can collect data at highway speed with sub-millimeter accuracy. So each pixel represents less than a millimeter squared on the road, which is great, but still the evaluation is manual. So someone has to grade those images, which has a number of problems. One is inconsistency. So if even one inspector inspect that 2 different times or 2 different locations, he will get different answers. It is subjective. Between 2 different inspectors, you will get different results. And of course, because a lot of work for a limited number of people, it is usually not that accurate. So several attempts have been made to make it automated. And we looked into the literature. What we saw was that almost all the proposed systems, computer vision-based systems to automate, or have these components: 1 image processing component, a feature extraction component, a machine learning component, and a pavement rating component. And I'm going to go through them very short, just to have a general idea of the automated or computer vision-based crack detection. So the first stage is the image processing. So a variety of techniques from thresholding, simple thresholding, to OTSU, to histogram of differences being proposed, but they basically are aiming at the same thing, and that is to remove the random background of the pavement. Because one of the main challenges is that the texture of the pavement is very random. We also have many random objects, like other defects or pavement objects in there, which makes it difficult. Also, the crack shape is very random, so we cannot make any rule about that to detect it. So all these methods try to remove the background. The method that we use as a baseline to compare our other methods is the one that is proposed in the paper you can see at the bottom. And it's based on bottom hat transform. What it does is that it removes the texture and extract everything that looks like a crack. Like other image processing technique, it has limitations. Most of the image processing techniques have this limitation that when you do the detection, the results come out fragmented. If you can see on the first image, the original image, we see one crack. But on the second image from the left, we see multiple detections. So it is detected in fragments. And that's the problem of fragmentation. And many methods being proposed in this paper. They propose the dilation, morphological dilation technique. Boundaries will expand and the crack will join. And they did an extensive study to basically find the parameters and prove their concept. And at the end, a thinning transfer can be used, so we can have an abstraction of the crack for the direction or calculation of the length. So after these challenges for image processing is answered, one main challenge remains, and that is we still have considerable noise in the processed results. As you can see in the crack grouping results, we have the main crack, but there are also so many noises, and that's why we need feature extraction or descriptors to describe these objects, and then use a machine learning and classification technique to separate the noise from the actual crack. So in the second step, we will have feature. Features are supposed to describe the objects that we detect. And when we looked into the literature, area, texture, and intensity were very popular features. Almost they were constantly used in all the papers. But we decided in order to be complete, we consider in 4 categories. The features that are describing the geometry, the ones that describe the texture, brightness, and position. And they are not only from the literature, but if any pavement management agency like AASHTO has some wheel path designation requirements, we try to formulate that also in the features. And one important feature, probably the most important one, is the width. Because not only for classification, but later when we want to rate the pavement, it's very important to know the width. Many of the crack rating systems are based on average width of the crack. And so just a side note on that. And one of the advantages of the image-based or computer vision-based system is that you have access to sub-millimeter accuracy images of the pavement. And if you can quantify the cracks, detect them, then you will have quantified statistics with sub-millimeter accuracy from the cracks. And here's what we visualized using these features. You can see the area of the cracks, the length of the cracks, orientation, and intensity. And these are things that are normally not available through a manual inspection. So you can have all of this for every picture, every image of the pavement. Using these features, the first thing we need to do is to remove the noise. And when looking at the literature, what we see is that most of the paper only report their successful rates, meaning the true positive and true negative errors, the cracks that are correctly accepted and the noise that is correctly rejected. But as I will go through more details, I see we definitely need some sort of error quantification and hypothesis test. We need to know how many cracks we missed and how much crack we missed and how much noise we accepted as crack. And that is something that should be considered and will be clear in a couple of slides. And after, of course, we train the network, we check the error rates and make sure that the results in an acceptable range and the detection results. So we detected the cracks. Of course, this one is produced with an ANN, with an artificial neural network classifier. As you can see, we can design the network to have different sensitivities. So if we train a very sensitive network, the one on the left with threshold 0.2, we detect almost all the cracks. Some marginal small cracks might be missed. The correctly detected ones are in blue, and the missed cracks are in purple. The false detections are in red, and the correctly rejected or the noise that is removed is in green. So as you can see, we didn't miss much, but that comes at the cost of some false detections because of the trade-offs between miscrack or error type 1 and error type 2 miscracks and false detections. On the other side, if we have a very insensitive network, we will miss a lot. You can see for threshold 0.8, we miss a lot of cracks, but we don't produce any false alarms. And they are the practical applications. But then at the last step, of course, the most important thing is how to do the actual or how to conduct the rating. Although the different states have different evaluation techniques, but what we found is that they have usually very much similarity with either ASHTO approach or ASTM approach. So using the features that we calculated in step 2, we not only can classify, but it also helps us in conducting the crack ratings. The ASHTO approach we considers will path designation, and we applied that. We implemented that for the pavement images. You can see top ones are the raw images and bottom ones are the analyzed one. Green is the low severity and blue is average severity. If you can see any red, that is high severity cracking. Some further examples. And of course the F-dot or the version that F-dot is using is from 1 to 10 rating, which you can see at the bottom, and I guess less than 6 needs replacement or some sort of treatment. And also we have ASTM, which is based on PCI, Pavement Condition Index. And using the features again, we can conduct this crack rating also. It divides into fatigue cracks and linear cracks, and low severity, medium severity, and high severity with a PCI number at the end. Of course, after we developed the system, we were very interested. It was a lab produced code. So we were very interested to know how would it work in a real world problem. And for that, we decided to apply it to a large scale data set. This is the city of San Antonio in Texas, which we got the data, more than 75,000 images, around 200 miles, from different zones or different traffic zones: collector roads, local roads, minor roads, and principals. And it's also only possible through our collaboration with the company called DTS, or Data Transfer Solutions, which does extensive data collection and pavement evaluation for different DOTs. Another advantage of the vision-based, after you calculate the PCI for each image, there is GPS tag for each image, and you can match them with the actual map. So you can see the more red the color of each image, and the worse the condition was based on the PCIs. And we can map them easily on the network. As you can see at the larger scale, you can see exactly which parts of the network has poor condition pavements, which are good, which is a very essential data for pavement management agencies to manage their roads, because they need to know how to allocate the budget. And for this budget allocation plans, a very detailed level, the computer vision based evaluations can provide those data. Not only that, but also the features that we calculate gives very detailed information about the cracks, average of the geometry, the shape, the orientation of these cracks, and doing statistical analysis on those parameters can also provide further information. For instance, we conducted the experiment on principal roads, as you can see, which is average, has with average traffic compared to some other ones. And Considering the orientation and the histogram distribution of the orientations, we can see most of them are distributed around 0 or 90 degrees, which show longitudinal cracks. We see very little 0 degree or transverse cracks, which means most of the cracks on these pavements were longitudinal. If you compare that with the collector roads, which have higher traffic level, you can see there is significant higher number of transverse cracks, which usually indicates we have fatigue in this pavement, or fatigue cracks are starting to develop in these pavements. So this information are the benefits that we can get mostly from vision-based system, and they are absent in a manual inspection. Of course, we conducted for all the different road types. And just as a side note, with recent advances in GPU computing and parallel processing, it is getting much faster, and we are getting much closer to real-time processing of the pavement data. This is a system developed by NVIDIA, which is hundreds of times faster than running on CPU. And as a matter of fact, we did a simple test for our procedure, which consists of bottom hat and filtering and morphling C, and then classification. And you can see the values, the time for CPU versus GPU. You can see for some of the computationally intensive categories like bottom hat or morphling C, the improvement is around 20 times faster, which is promising. And so that is basically a promising way that we can conduct faster and faster for larger networks automatically. But the focus of the paper that we submitted and got accepted was the machine learning part. So all the procedures that I explained, image processing, feature extraction, machine learning, and pavement rating, the paper includes our search for the optimum machine learning technique. And when we say optimum, we don't only consider the performance or prediction accuracy. We looked at the literature. There are a lot of methods that have been used. K-nearest neighbor was used, decision trees were used, adaptive neurofuzzy inference systems were used. Of course, support vector machines and artificial neural networks were used. Other than accuracy, we were also very interested how much computation time, because at network level analysis, that becomes very important. But other than that, the challenges and the usual challenges of image processing and using computer vision for this task, one of them is imbalanced data set. We will always are dealing, when we collect the data set and we separate the cracks from the non-cracks, the data is always imbalanced, because usually the number of cracks should be always less than the clear pavement. And for all the methods that have been proposed, or all the techniques that have been used, they're all dealing with an imbalanced data set. And that's a well-known problem in data science, because we know imbalanced data sets can hurt the accuracy and performance of the classifiers. That is something that we had in mind. And the other thing is that when we train one network, one classifier to detect cracks, we are very concerned that if we apply it to clear pavements, it might overestimate cracks. And if we apply it to a very damaged pavements or poor condition, it might underestimate. So we wanted to make sure that the classifier can provide consistent and correct results for different pavement conditions. And also, we were also interested to know how much information can we get from the classification procedure. Is there anything from interpreting the classification procedure that we can use for pavement, from pavement point of view, pavement management point of view? So these are the criteria that we consider. Of course, the classification methods are that we considered. I list them here. I have backup slides if you have detailed questions about them, and we can discuss them. But they are ANN, KNN, and DT have very simple logic. They are basically called white box methods because following their logic is easy, while the ANN is a total black box. We don't know what happens in that classifier. We just give in the inputs and get the outputs without asking what happened inside. Adaptive neurofuzzy, I will explain it. It is more clear than ANN, and that can be might be helpful. But how do we train? For training classifiers, it is important, of course, each classifier has different parameters, training parameters that should be considered. That is one parameter. The other thing, as I mentioned, the imbalanced data and the challenges that it will cause. And the last part is how do we partition our data set? So we should dedicate some data for training, some for validation, and some for test. What are the challenges there and how we can deal with them? So I go through them one by one. For the training parameters, it's a well-known problem for all the neural network-based methods. You can overfit your training data. And we can see here, I schematically can present that. If you have a training data set and you train the network, of course, the training error is going to reduce as you train. But after a certain threshold, you start to overfitting your training data. And that is because your model is becoming too specific to your data set. And you can know that by watching the validation error. So you apply to a completely independent data set, and the error first starts to drop. But after a while, because the model is losing its generalization ability, the error starts to increase. And that is one parameter, training iterations, or the amount of training for ANN and ANFIS is the critical parameter that should be considered. For decision tree, this key parameter is the depth of the tree. If we have a very deep tree, the error of training will be low, but we lose generalization and don't get accurate results at the end. For KNN, it's the number of effective neighbors. We consider all these, and there is comprehensive description about them in the paper. But I just want to say that we did a parametric study and tried to come up with the best parameters for this analysis. The imbalanced data, which I emphasized several times, is that, as you can see, even in the image, we have multiple. These are the results of image processing. And the noise that we have to deal with is many times larger in number than the number of cracks. And also I have the quantification. As you can see, the number of cracks is here and the number of all objects are here, which is a huge difference, which means the data set is highly imbalanced. And it's a well-known problem in data science because when you have imbalanced data set, the cost of misclassification is not the same for both classes. You have one class that has more members, and the sum of cost of misclassification will be higher for this class. So losing cracks will not affect the training that much. Of course, there are many methods to deal with it in the literature, data level methods like random undersampling or oversampling or directed sampling. There are also a limited number of algorithmic levels, like cost-sensitive learnings, basically, but they're not available for all the classifiers. Another problem with the imbalanced data set is that when you partition your data, or when you dedicate some samples to training, some samples to validation, and some to test, sometimes your training, in extreme cases, can contain no tests, no samples from the other group. And sometimes the statistics of the two classes are very different. Then you are training for something and applying to something completely different, and you cannot expect good results. To deal with all this, we proposed a specific data partitioning technique in which we do not randomly select the samples, but separate the cracks from non-cracks, or each classes, and then divide them to whatever portions that we want. Here is 60, 20, 20. The thing is that after combining these two, we can ensure that the training, the validation, and the test data set always have a fixed ratio of cracks and non-cracks in them. And therefore, we always have samples in our training and validation and tests. Considering all these parameters, the training parameters, the data partitioning, the oversampling, we applied the classifiers. The first thing I wanted to say is that we repeated classification many times to see that this partitioning technique is working. If it's working, the variation in the results should not be significant. And as you can see, for each of the parameters that are calculated. All the classifiers provided consistent results, which means that the partition technique is, we consider it satisfactory. But the interesting thing is that if you look at the y-axis or successful classification, all of them provide more than 98% accuracy. And I even summarize that here. At the beginning, I said when we got here, we were surprised that all the methods, however simple or however complex, they can provide similar results. But that is because only reporting successful classification is misleading. We need to have some sort of error quantification and hypothesis test. We need to know how many cracks we missed, what is the percentage of cracks that we missed, and the percentage of errors that we produced. Also, we noticed that the number, which is very popular in computer science, reporting in number is not a good measure from pavement perspective. We are more interested, we are very concerned not to miss any long crack. Maybe losing a couple of very small cracks is okay, but we definitely don't want to miss large cracks. And just reporting the number does not represent that. Therefore, we converted all the error ratings and all the error quantification into length, and we also conducted the hypothesis test. So you can see for different methods, we have for training, validation, and test, we have the error based on length of the cracks. And then now it is much more clear. We can see even KNN is missing all up to 50% of length of the cracks, which means it cannot be considered acceptable, because the sole purpose of a crack detection system is to detect cracks. And if we miss half of them, that is no longer an acceptable system. For DT is also very high. ANN and ANFIS provide very much more acceptable results, less than 10% in most of the cases, both false alarm and miss cracks. Therefore, we consider them better methods. They have enough complexity to handle the nonlinearities in the data. I also summarize the results in here in the table above, and you can see the 50% and the almost 30% of missing cracks for those two methods. The second criteria for us was computation time. We noticed, as we expected, the decision tree and k-nearest neighbor techniques, they are very simple methods. They don't have much adaptive parameters. And of course, the training time for them is much less than methods like ANFIS. ANN and ANFIS generally take more time to train because they have more adaptive parameters. Especially for ANFIS, the whole process of fuzzification and defuzzification takes a lot of time. But I should just emphasize that these are just training times. The inference time or the time for testing a model, for all of them are basically the same. So in application or in real world application, they will all perform almost similarly. And our last concern are the classifiers going to provide consistent results for different pavements. So we apply them separately to each pavement type separately. As you can see, all of them almost provided. The blue one is the good pavements, so they had no cracks, they were very clean. The red ones had some linear cracks in them, and the green ones had block cracks or alligator cracks, severely damaged pavements. And as you can see, all the classifiers almost provided consistent results. So the accuracy or the performance didn't change drastically from one pavement type to the other, which we consider satisfactory. And just as a side note, as I said, we were interested to know how much information can we get. And unlike, of course, we set aside DT and KNN because of their prediction performance. ANN is a total black box, as I said. But ANFIS, when we trained it, there are membership functions that get trained. And if you look at the membership functions, we can infer basically some ranges. What we see here is that the first membership function is high, both membership functions are average, and then the second membership function has high values. We can verbally describe three categories here: the lengths that are small, the samples that the length is average and where the length is large. And we can do that for all different features that we measure. The good thing is that this is a good measure to convert between quantitative values and verbal descriptions. And that is important because many of the descriptions in the pavement evaluation methods are descriptive. For instance, in H2 or in F-dot, we have low spalling or moderate spalling or severely spalled cracks, but they don't give any specific quantitative measure what is the low spalling. And this sort of analysis and this sort of fuzzy logic can help us go between quantitative values and verbal descriptions. So it is something that we consider can be interesting for future studies. And of course, the conclusions, we considered the classifiers for different criteria. What we found was that although decision tree and k-nearest neighbors are simpler, faster, but they might provide significant false negative or missed cracks. Artificial network and ANFIS usually take more time, but they are more accurate. And ANFIS might be able to provide further information for us that can be helpful. And we also propose different notes. For instance, error quantification is essential, or seeing the error values in terms of crack length is very important for us. And we didn't find any inconsistency in the performance of classifiers for different data types. But before I end it, I thought maybe I talk about some other methods that we haven't seen as much in the literature and sound very interesting, and like convolutional neural nets, especially with the popularity of deep learnings recently. These methods can be very effective for pavement evaluation. That is because if you remember, the 4 stages of most systems are image processing, feature extraction, machine learning, and pavement rating. And if we use a deep convolutional neural, we don't have to do any image processing and feature extraction, which are huge burdens, because designing the features and controlling the image processing parameters and conducting that is not only time taking, but also because they are based on human inference, that is going to be always have some errors in them. In the deep learning and the CNN technique, the computer automatically will learn what type of image processing are required and apply them, and what type of features are most effective, and it will learn them automatically, which can be very advantageous. I don't want to go into the detail, but basically CNN is just a series of convolutions and pooling systems or subsampling. I just wanted to share some results that we did. As you can see from the left to the right, we used deeper and deeper networks, and you can see on the right hand side we have clear detection of the crack parts. The good thing is that it can easily also be expanded into other type of defects like markers, like manholes, basically like potholes and other type of defects, and of course patches, which is a part of, and that's something that we are currently considering for research. I guess that's all the materials that I had, and thank you.
Thank you, Dr. Mokhtari. Very interesting. Any questions from our audience? Right, I actually have a few questions. So I'm assuming that you've done this based on images, not like still images, not video images. Is this correct?
That's correct. That is correct.
What is the possibility of applying the algorithms to video images?
There are video processing techniques that computer vision scientists are using. That is most of the techniques are basically frame by frame analysis. And the good thing is that these of MPSVs, they basically cut the long image into fixed spaces, and they're after each other. So if anyone, I guess that sort of solution can be more advantageous for like road sign detections, because then we can see, and that is something that the camera distance is not fixed, and from the correlation between different slides, it can really help. But since in the pavement, the condition has been perfected, so we have fixed distance and we have a constant resolution over all the pavement image, I think using still images might be more advantageous. In recent years, of course, I guess you know that industry is moving toward 3D imaging, because 3D imaging has depth information, and depth is very critical, because if we know that this part of the pavement suddenly there is a drop in depth, that can help really detecting cracks more accurately. But in terms of video processing, I guess they are limited to road sign detection and those kind of asset management, pavement asset management problems.
Right. Thank you for your answer. Now, I do have an observation about the performance of the test data.
Uh-huh.
It appears that the success rates on the training and the validation data sets was lower than the test data in both the artificial neural networks and the fuzzy inference, which I thought was very interesting.
Is it this slide?
Yes. So in the next slide. Yes. So in the artificial neural networks and the fuzzy inference, that was the classification error. All right.
These are classification errors. Yes, and the thing is that usually 5-6%, because it's every time we started training a classifier, basically the backpropagation and those gradient descent training, it starts from a different point. We usually never get exact same results.
No, I understand, but looking at the success rates, which is the first three columns, so it looks that the green, which is the test data set, had a slightly higher successful classifications than both the training and the validation data sets.
Training and validation data sets. For ANN and ANFIS, right?
Yes.
Yeah, yes, I guess, but yeah, you're right. It seems that the ANN and ANFIS success, I guess, success in DT and KNN looks a little higher.
Which one? ANN?
The upper ones, the decision trees and k-nearest neighbors. They are.
I'm looking within ANN, within the artificial neural networks alone. The first three columns, so the successful classification in the validation data set was slightly higher than the training. So the red column is slightly longer than the blue column.
Yes.
And in the green column, it's even, so in the test data set, it's even higher.
It's higher than it's probably because of the validation process, because it stops the validation process. But I cannot come up with the reason why that one is higher, because we control the classification. We don't want to overtrain. We don't want to overfit the model. But the reason why that is, I don't see that is very significant. I don't know if you think that's significant, maybe 1 or 2%, but I am not sure why that happens.
No, I don't think it's significant. I think it's just very interesting, because one would imagine the trend to be, so the data that you use to train the model, I would imagine that the success rate in this data would be higher than the success rate in a new data set.
You mean test data, right?
Yes.
Yeah, because we control the training. We don't allow, I guess I explained it. We control basically the training procedure. We control the procedure. So, and if we continue that, the model will fit completely to training, and the error will reduce. But we control it somewhere before the overfitting happens, and then to maintain the quality of validation data. But I guess the error there is basically the difference between them is not significant. It basically shows that it consistently over training, validation, and test provided almost similar results.
Yes, which is very interesting. My other question is, how many images did you use, and did you fit a model? So did you train a model for every image and then apply the model to the same image, or did you train a model for just one image and apply it to 1,000 other images?
For the application, for the large network that I showed, we trained 400 images. We trained 400, which were in the order of hundreds of millions of cracks and noises. And we use that, we divided into 60, 20, 20, 60 for training, 60% of entire data for training, 10% for validation, and 24% for test. But for the proof of concept, or the one that we did in the lab, we only used 30 images. And I think I showed the statistics somewhere. The numbers only somewhere around here. Oh, here is it. So here are the images that we use only in the lab as a proof of concept. You can see we selected them from different conditions: poor condition, average condition, and good condition. And you can see there's a huge difference between the number of cracks and non-cracks. But we had the ones with low cracks, or basically clean pavements, average ones, and highly severely damaged ones. And we used all of them and the entire data set. And then we used the stratified partitioning. We partitioned that into 60% for training, 20% for validation, and 20% for test. And we repeated this randomly for 10 times to make sure that there is no parameters that can cause inconsistency or a biasness in the training.
Excellent. Well, thank you very much.
Thank you.
Any other questions from our audience?